Introduction today to all of the properties that isomorphisms preserve. This is a combination of Theorem 6.2 and 6.3 in our book. Essentially, isomorphisms between two groups preserve any property that you can imagine. Let me remind you what an isomorphism is. An isomorphism is a bijective map phi from one group G to another group H, and it also preserves the group structure. So if I have two elements A and B in my first group G, then combining them in G and then mapping them over to H via phi is the same thing as first mapping A to H via phi and mapping B to H via phi and then combining them together in H. So here, G and G bar are going to be the names of my two groups, and phi is going to be the isomorphism between them. The only difference in notation is I'm using G bar instead of H here. G bar is not the group we constructed in the proof of Cayley's theorem last time. Okay, so we have an isomorphism phi going from a group G to another group G bar, and it preserves essentially any group theoretic property you can think of. Let's list a couple. The identity in G necessarily gets mapped by phi to the identity in our new group, G bar. Similarly, if you raise an element A to the nth power and then map it over, that's the same as mapping it over, phi of A, and then raising phi of A to the nth power for any inputs A in our first group and powers n. Two elements, A and B, commute in our first group, G, if and only if their images, phi of A and phi of B, commute in our new group, G bar. G is cyclic, generated by an element A, if and only if G bar is cyclic and generated by phi of A. The order of an element, so the smallest integer n, such that that element to the nth power is the identity, the order of an element is the same as the order of its image. If phi is an isomorphism going from G to G bar, then the inverse map, phi inverse going from G bar back, is also an isomorphism. If two groups G and G bar are isomorphic, then one is abelian if and only if the other is. We essentially already mentioned this, but if two groups G and G bar are cyclic, then if two groups G and G bar are isomorphic, then one is cyclic if and only if the other is. Another important property is that if H is a subgroup of G, then the image of H, namely take all your elements in H and apply phi to them, that's a subgroup of G bar. Okay, so this is a long list of properties, but read them over, think about them, and ask me if you have questions on what any of them are saying. Okay, since two groups being isomorphic means so much of their structure is preserved, we now have many ways to show that two groups are not isomorphic. Indeed, if any of those structures that we listed above are not preserved, then the two groups necessarily cannot be isomorphic. So if two groups have different sizes, then certainly they're not isomorphic. There's no bijective function between two groups if they have different sizes. If one group's cyclic but the other's not, then they can't be isomorphic, because we saw up above that if two groups were isomorphic, either they were both cyclic or neither of them were cyclic. So if exactly one is cyclic, then and another group is not cyclic, then they can't be isomorphic. Similarly, if one group G is abelian and another group G bar is not abelian, then G and G bar cannot be isomorphic. And we saw that in a group G, under an isomorphism, the order of an element A was the same as the order of its image, phi of A. So if in one group G, the order of an element is larger than the order of any element in the second group, G bar, then G and G bar can't be isomorphic because A has no element of the same order in G bar that it could be mapped to. So let's discuss how might we show that these groups are not isomorphic. These groups being Z12, the integers mod 12, D6, the symmetries of a regular hexagon. You should ignore the colorings. A4 is also a group. It's the it's the alternating group of permutations of 4 elements. So S4 is all permutations of 4 elements. A4 is the even permutations, those permutations that can be written as an even number of 2 cycles. Okay, all of these groups are of the same size. All of them have size 12. In Z12, our elements are from 0 up to 11. We have 12 numbers there. In D6, we again have 12 elements. We have 6 different rotations, and we also have 6 different reflections for a total of 12 elements. A4, the alternating group, also has size 12. Remember that A4 has half of the size of S4. In general, AN has half of the size as SN because half of our permutations are odd and the other half are even. The size of Sn was n factorial, so the size of S4 is 4 factorial, or 24. A4 has exactly half that many elements, so it has size 12. So just by looking at the sizes of these groups, we can't tell them apart. They all have 12 elements. Okay, so we don't yet know whether they're isomorphic or not. However, there is a way to distinguish these groups. It turns out that the element of largest order in these groups is respectively of order 12 in Z12, of order 6 in D6, and of order 3 in A4. So in Z12, it's cyclic. The element 1 is a generator, and the order of element 1 is 12, right? 1 plus 1 plus 1 plus 1 dot 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 is never equal to the identity until you've added 1 together 12 times, and then you get back to the identity. In D6, well, all of the reflections have order 2, because if I do a reflection twice, I get back to where I started. But the rotation, just by 1 step, that's an element of order 6. 1, 2, 3, 4. Let me try that again. Okay, black's on top, and I rotate 1, 2, 3, 4, 5, 6 times to get back where I started. So in D6, there are elements of order 6, but no elements have higher order. In A4, it turns out that the highest order you can get is 3. A 3 cycle has order 3, and a 3 cycle is a product of 2 cycles. It is an element of A4. So as long as you believe me that the elements of largest orders in these groups have orders 12, 6, and 3, then by this last bullet point here, we've proven that these groups are not isomorphic because the orders of their elements do not match up. Another example of this, we already saw on page 51 or 52 of our notes that the rational numbers under addition is not isomorphic to the rational numbers that are non-zero under multiplication. And you can go back, and it was page 51. You can go look at page 51 to see the first proof we gave of this. Here's a slicker proof. I forget if I said integers or rationals. Hopefully I said rationals on the video, but we have the rationals under addition and the rationals that are non-zero under multiplication. Okay, in the rationals under addition, every non-identity element has infinite order. So the identity here is 0. And if you take any element that's not the identity, like 2/3, and you add it to itself a bunch of times, 2/3 plus 2/3 plus 2/3 plus 2/3, you never get back to the identity. So it has infinite order. By contrast, in the non-zero rationals under multiplication, there's an element which has order 2. -1 has order 2. -1 squared is equal to 1, and 1 is the multiplicative identity in this multiplicative group. So that's maybe slicker verification that these two groups are not isomorphic. In the rationals under addition, we have that every non-identity element has order infinity. Whereas in the non-zero rationals under multiplication, we have an element of that's not the identity that has finite order. -1 is not the identity, and it has finite order too. So since these groups don't have elements of all the same orders, they certainly can't be isomorphic. All right, thanks for watching, and let me know what questions you have.